All right, let's jump into today's actual topic. So today we're going to get into our first criterion, input space partitioning or input domain modeling, if you prefer that term. I use them interchangeably. So I want to start off, this is a year old, but it's still hanging out there. So hint, hint, I know we did, I know we did your favorite software failures. We talked about that at week 1 or week 2. You should always feel free to go ahead and post about something that you find in the news, because I'm always happy to, to bring in the news things. So this was actually from February of 2020, when the world was still kind of a different place. NASA finds fundamental software problems in Boeing's Starliner spacecraft. The software problems almost resulted in a failure of, thankfully, unmanned test mission. The best part of this article was this quote here. Now, Lavero, I forget who Lavero was, whether he was Boeing or whether he was NASA. Bottom line is that industry is very bad at doing software. Ouch, but also true. So where are we? A year later, we're in February 2021. Boeing has added at their own expense a second unmanned test launch as a result of these problems to verify that they're all fixed. And as of 1 year later, that second launch has not yet occurred. So, they're a year late, on their overall schedule with a launch that they need to fund themselves as a result of this. So pretty bad scenario. So there you go, a little software in the news, and I'm always happy for more. All right, so tonight we're going to be talking about input space coverage. So here we are with our graphic that we'll see most weeks from now on, which is kind of the structure of the book. And we are over here in the input space category. So what are some of the benefits of input space partitioning? And don't worry, we're going to come back and talk about what input space partitioning is. So first of all, it can be applied at a lot of different levels. This is a technique you can use for unit testing or integration testing. You can use for system testing, right, at all different places along that verification V diagram that we've talked about a couple of times. Pretty easy to apply without heavy automation. This is not really a heavy mathematical thing. This is really kind of based on domain knowledge and domain expertise. It's pretty easy to adjust the criteria to give yourself more tests or fewer tests. And so you can adjust that and have a methodical way of adjusting your tests, right? We talked about how the amount of effort and investment that you're putting in your tests should be based on the probability and consequence of failure of your system. And so this gives you a way that you can kind of easily turn that dial up and get more tests, or turn that dial down and get fewer tests, and adjust your testing effort to the level that you think is satisfactory to the system that you're testing. And that honestly is kind of an art form. I mean, knowing what the right level of testing is. Okay, 10, is that too many or is that not enough? That's kind of an art form. That's a hard thing to give hard and fast rules at. And then last of all, no implementation knowledge is needed, right? We don't need to know the source code implementation. And in fact, we don't want to know the source code implementation when we're using input space partitioning. We want to be thinking about this thing as a black box. We want to have an understanding of what it's supposed to do. We need to have an understanding of what kind of inputs it takes, but we don't really care about the implementation. And if I hadn't previously said so, I think I may have in a previous slide. This is a great approach to combine with other testing approaches that do require implementation knowledge. So for example, if we were doing statement coverage, or like the testing that you did in this last assignment, right? You're doing that testing based on looking at the code. Doing that testing looking at the code is pretty effective at finding things that you've done wrong, but it's pretty bad at finding functionality that you missed, right? Functionality that didn't get implemented. Because if you're basing your tests off the code and there's no code to do something, then there naturally won't be any tests for it either. This kind of input space partitioning testing kind of backs you away from the code, lets you think about what is this thing supposed to do and what should the inputs look like. And so this actually gives you a pretty good tool to find errors of omission, right? Things that you didn't implement. So when we're doing input space partitioning, this is all about taking an input domain and partitioning it into a set of blocks. So given some domain D, which means all of the possible inputs, we want to come up with some partitioning scheme such that we have a set of blocks that satisfy two properties. First of all, these blocks, which in this diagram are the B1, B2, B3, that whole rectangle is the total input domain. The blocks have to be disjoint, meaning there's no overlaps. There's no possible test value that will fit into more than one of the blocks. And the blocks have to be complete, meaning that together they have to completely cover the domain. In other words, there's no possible value that doesn't fit into one of the blocks. So we could combine those two and say every possible value must fit into exactly one of these blocks. So disjointness and completeness, those are the two key characteristics of breaking up our input into partitioned blocks. So when we are using input space partitioning, we're going to be making a couple of assumptions. When we're actually using this approach to write tests, we're going to choose a value, usually one value, but possibly more, usually one value from each block. And we're going to make the assumption that all of the values in a partitioned block are equally useful for testing. If they're not equally useful for testing, then we should probably draw our partitions differently. So for example, if I had an input space of integers, I might decide to break that input space of integers into 3 blocks. And I might say one block is all integers less than 0, and one block is all integers equal to 0, which of course is exactly 1, and one block is all integers greater than 0. So I'm disjoint because no integer can fit into more than one block. I'm complete because every integer will fit into one block. And now when I do tests, when I write tests, I'm going to pick a test value that's less than 0, and a test value that's 0, and a test value that's greater than 0. And I'm assuming that all of the values that are less than 0 are as good as any other value that's less than 0, right? Each of those that are in that block, it doesn't matter which one I pick. They're all pretty much, I expect them to act the same. If I don't expect them to act the same, I should break up the block differently. So how do we apply this to testing? Typically what we're going to do is we're going to try to find some characteristics that define the input. So that might be parameters to a function, which is probably the most common thing that we're going to be doing, in our kind of smaller examples. But we might be looking at, kind of broader descriptions of what the input domain is. Then we're going to create tests by combining values from those characteristics. So going back to my integer example that I just gave, let's say I have a function that adds 2 integers. If I wanted to test that, it takes integer I and integer j. I might make a test that where I is less than 0 and j is less than 0, and I is less than 0 and j is 0, and I is less than 0 and j is 1, and I is 0, j is less than 0, j is 0, j is greater than 1, right, etc. I could do all those different combinations by, for each of the variables, picking one value from each block. So what are some example characteristics? We might have a characteristic that says this input X is null. And in that case, based on that description of the characteristic, the values for that characteristic would probably be, true or false, right? It's either null or it's not null. We might say, okay, I'm processing a file and the order of items in the file matters. And I'm going to define the order as sorted, reverse sorted, or random, or maybe more choices. Or maybe I'm selecting an input device, right? My code that I'm using requires that I select an input device. It takes that input device as one of its inputs. So what are my possible input devices? And I will enumerate them. I've got a DVD, I've got a CD, I've got HDMI, I've got RS-232, I've got, whatever other inputs there might be, and I'll enumerate those. And each of those will be a block. In that case, each block consists of exactly one value, right? The DVD block is DVD. The CD block is CD. So how do we want to choose partitions? Because when we take that input domain, we want to break it up. How do we go about breaking it up? And it seems easy at first, but actually it kind of is a little harder than it at first seems, and it's easy to get wrong. And your input partitioning will really define all of the testing that happens afterwards. So this has to be thought about very carefully. So let's go back to the order of a file. So I've got some file and I've decided that it can be in ascending order or descending order or random order. But what if the file has one item in it? A single file, a single item could be considered sorted ascending or sorted descending or sorted in, random, unsorted. So the example of a file that contains one thing could be in all three blocks. So this category or this partitioning is not disjoint. So if they're not disjoint, if the partitions aren't complete and they are, or they aren't disjoint, then we really haven't thought it through carefully enough. So we need to actually spend a significant amount of time, doing a fairly thorough analysis on our input space and on what our partitions are. And just like in an environment, if you're doing this on your own, then like any code you write on your own, you review it yourself. If you're doing it in a group or doing it as part of a workplace, typically in a workplace, you're going to write code and that code is going to go through some sort of code review, right? Other people are going to look at it. Just like we'd be reviewing code or other artifacts, we should be reviewing partitioning, right? Which is really a test design artifact. We should be reviewing that in the same kind of way.
Professor, small question regarding the previous slide.
Mm-hmm.
So while considering partition, the sets have to be disjoint, like they have to be disjoint and they cannot have any similarities like that.
So you have to define the partitions so that the blocks in the partitions are disjoint. So let me go back to this example, and I might cover this on a future slide, but I'll talk about it now. So if we said that we have three partitions, right? We partitioned the order of file into three things: ascending, descending, and random. And then we realized, well, wait a minute, a file of length 1 fits in all three of those. So now I need to change the partitions. So I might add a new block saying a file of length 1. And then I may change my other three to say a file of length greater than 1 that's sorted in ascending order, and a file length greater than 1 that's sorted in descending order, and a file length greater than 1 that's sorted in random order. While I'm doing that, that will resolve, right? That will resolve that problem. Although while I'm doing that, it may also occur to me, hey, now that I'm thinking about a file of length 1 as kind of a special case, what about an empty file? Is that, oh, that doesn't actually fit into any of those categories. So now I need a fifth block that's empty file. And now, arguably, thinking about it for, 15 seconds here, I have possibly, I'm not even sure I'm willing to say probably, but I have quite possibly covered all the possibilities of the file, right? It's empty, it's got one thing, or it's got more than one thing and is sorted in ascending, descending, or random. So that's how I would adjust my, my partitions so that I can make them complete and disjoint.
If we do that, there might be possibility of getting a lot of disjoint groups. Will that be a problem?
You could potentially have, you're talking about the number of blocks expanding,
Yeah.
right? Getting more and more blocks. Yeah, you can get more and more blocks, and that's okay. Although if you start to get, more than, there's no hard and fast number here, but if you were up at like 10 blocks, I'd be tempted to start thinking about whether I'm looking at my input space the right way or whether I should take a different view, because 10 for any particular characteristic would start to feel like a lot.
Yeah, I thought the same. I think I got the hang of it. Thank you so much.
You're welcome. Thanks for the question. All right, so how are we going to go about doing this? So if we've got a piece of software, we want to think about how are we going to model the input domain, where do we start? And our first step is we want to identify, okay, what are the things I'm going to test? So let's say that we're testing a class. I might want to look at what the methods are in that class. And let's say I have a list class, right? And my list class has add and delete, for example. Okay, great. I've got two methods. The methods will often have the same characteristics, right? So if I might have an add and I might have a find. Well, add takes an object and find takes an object. So that characterization, right, that characteristic of what does an object look like, what blocks, what partitions are there for an object, I may well be able to reuse that between add and find, because I might be able to see the same kind of thing, right? I can try to add null, or I can add a single object, or I can add an array of objects, whatever, and that same thing may apply to find. So when we start looking at entire programs have a lot more characteristics. And when we scale that up to systems, now we may have, thousands of characteristics. So if I look at a healthcare management system, for example, wow, what's my input domain? Well, I'm going to have doctors and all of their data and patients and all of their data and different facilities and what capabilities the facilities have, how many beds they have, do they have an x-ray machine, do they have a CAT scan, right? And you can start to see that as you get up to big systems, modeling all their possible inputs can actually become quite a big job. And this is actually a challenge for a great example of this would be Android developers. If you're developing on Android, you have, how many devices? And all of the devices are different, and how many versions of Android, and how many OEM versions of Android, right? Because Google Pixel is running the straight Google one, or maybe it's not, and Motorola is putting their own version on it, and somebody else is putting their own version on it, and you start to feel like, wow, there's a massive number of combinations here. So once we've found our testable inputs, then we want to identify what are the parameters. And this is usually pretty straightforward, right? This is usually kind of a turn the crank kind of activity, okay? We're calling add. What does add take? Well, add takes an object. What could an object be? Well, it could be null, or it could be an actual object, and maybe it could be an object of various classes. We can look at argument lists, for example. Argument lists are usually a pretty easy place, but we may have relationships between the variables. I'll come back and I'll talk to that in a little bit, because I think it's easier to understand by an example than it is for me to try to talk about it in the abstract. We have special values. We always want to be thinking about special values. Null, right? Null is almost always a special value we want to be thinking about. 0 is often a special value we want to be thinking about. Throwing an exception is often a special value or a special behavior that we want to be thinking about. So we're not using program source code when we're doing this. And I say that with a little bit of a caveat, right? A little footnote, because if we're looking at the code to identify what the methods or what the parameters are, well, obviously we're looking at the source code to see what the parameters are. The key point that I'm trying to make is that we're not looking at what happens with them. We're just trying to identify what the inputs could be. So when we're looking at methods, we could be looking at the parameters. We might be needing to consider what the internal state of the system or the class is, if it has any internal state. And as we scale up, from methods to components. Now, when we're looking at components, we may have many methods or many classes that we have to think about their inputs. We might have many state variables, right? We get to more and more complex systems, more and more complex collections of inputs and states. And if we might be thinking about, what could be in a database, right? My method uses an SQLite database. Oh, well, what are the tables in the database and what are the columns in the database? And you can see that our possible set of inputs continues to grow the more complex our system gets. Once we have identified all of those inputs, now we want to make a model of that input domain. So this is where we're going to say, okay, what are those parameters? What are the inputs? What are the states? What are the things that are in the input domain? And how should I partition them into blocks? And again, as I said, each block has some set of values that it contains, right? So I'm taking a single parameter, I'm dicing that parameter up into a discrete number of blocks, and every one of those blocks has one or more values in it that could possibly be in it. And we want those blocks to be disjoint and complete. So this is kind of the creative work, right, in input space partitioning. The previous step, finding the inputs, pretty mechanical. I look at the code, right, I can see what the parameters are, what the arguments are. This is the step that requires us to really kind of think, and often requires us to iterate. We'll often say, okay, I have my first draft of this input domain model, and now let's think about building tests. And I get to my second or third test and I say, oh, wow, that doesn't seem like a good combination. I need to go back and rethink, right? And so we'll go back and we may iterate a few times. So generally speaking, it's often better to increase the number of characteristics and decrease the number of blocks. That tends to help us lead to fewer tests. And some of the strategies for coming up with blocks include thinking about valid values or invalid values or any kind of special cases, right? Edge cases, boundary cases, or, going back to terminology we've used, what's the happy path, right? If I have a function that adds an item to the list, what's the happy path here? Well, the happy path is I pass it a legitimate object of whatever type it's expecting, right? That's the happy path. So I should have some, happy path block as part of my input partition. Okay, once we've built that model, we've got our domains, they're partitioned up into blocks. Now we can choose a test criterion to figure out what our test combinations are going to be. Any particular test input is going to have one value for each parameter. So going back to my example where I'm adding two integers, I've got an integer parameter that I've broken up into blocks, and I have another integer parameter that I've broken up into blocks. They may or may not be the same set of blocks. For the moment, we'll assume they are. What's a test input going to be? Well, test input is going to be a value for I and a value for j, taken from one of the blocks of I and taken from one of the blocks of j. And the example that I gave earlier, well, let's just choose all the combinations, right? I is less than 0, j is less than 0, I is less than 0, j is 0, etc. As we build our way up into real input domain models for anything with any complexity, choosing that, let's just do all the combinations, that is usually infeasible. And here I'm actually using infeasible in two ways, and maybe I should be a little more clear on this slide. First of all, it's usually impractical because the number of combinations just explodes into enormous numbers. It's also infeasible in the sense that typically you can't have every possible combination of every possible input, because often if I pick, DVD as my input, then files greater than 4 gigabytes can't be something that I match with it because a DVD has a 4 gigabyte limit, right? So I can't have an 8 GB data file if I had DVD as my input. So there are infeasible combinations, and we will talk more about infeasible combinations as we go. Then the last thing we do is we take those combinations of blocks and then we refine them into test inputs by choosing appropriate values for each block. So if I came up with a combination that was I is less than 0 and j is less than 0, now I need to come up with a specific input. So I need to pick some specific value for I that's less than 0. -5. And I need to pick some specific value for j that's less than 0. -1 million. All right, and there now I have an actual test. Now we can also use some test optimization tools to help with this. This will be an upcoming homework exercise. Using some combinatorial, right, some mathematical test techniques to dramatically reduce the number of tests that we have while preserving the kind of the distribution of tests over the input domain, so that we are reducing tests as much as we can while increasing risk as little as possible. So there are two different approaches to creating an IDM, an input domain model. We can use an interface-based approach, right? And this is simply, okay, I'm looking at my adder function, and it's got an integer I and it's got an integer j, and what integers look like, and I can block them up like that without really caring about how they're used, right? This is a pretty simple approach. There are sometimes automated tools that can help you with this, although it's pretty straightforward to do. We might also have a functionality-based approach where we need to have a better understanding of what's happening inside our the system that we're testing. So instead of an adder, where I'm adding two integers, let's say I'm testing a divider where I'm dividing two integers. Well, I may still decide to break my input domain, my integers, up into the same kind of values. But now with dividing, 0 kind of takes on a special case, right? Because divide by 0 gives us an undefined result. So as it happened, I happened to have 0 in my previous discussion of this as a block, because 0 is often a special case. But thinking about what's happening in here, oh, I'm dividing these numbers, that may force me to come up with a particular special case, a particular breakdown of the blocks to make sure that I can handle those special cases. Because I'd sure hate to have a divider and build up a set of test cases and my test cases never checked for divide by 0, because that's a kind of a pretty important thing in division. So I'd like to have an input model that forces me to think about doing divide by 0, or what about 0 divided by 0? All right, so first, let's look at this interface-based approach, right? We're going to kind of mechanically consider each parameter, right? We're going to look at each parameter and we're just going to kind of follow our set of rules to come up with a block for it. Pretty simple technique. Although it's important to understand that when we're doing this, there's things about our system that we're not thinking about, right? So I might be saying, okay, this is my math function. It takes two integers. What do integers look like and how should I break them up? Without regard to thinking, am I dividing? Am I multiplying? Am I adding? What am I doing with these integers? Well, we don't care when we're taking this approach. We're just going to think of them as kind of, this is just an input thing. And we're going to ignore the relationships between them. So let's see what happens when we do that. So we've got this class called triangle type. And the triangle type has a triang method, and we pass in the lengths of 3 sides, right? And we have simple triangles here. Our triangles have integer lengths to them. We're just kind of keep it easy here, right? Not all triangles have integer lengths, but ours do. And we're going to return what kind of triangle it is, right? And a triangle is either, okay, think back to your, 3rd grade geometry. These are words that, I know I hadn't used in a long time. Scalene, a scalene triangle, that's a triangle with no 2 sides that are the same. An isosceles triangle has 2 sides that are the same. An equilateral triangle has 3 sides that are the same, and an invalid triangle is a set of lengths that I can't make a triangle out of, like, 1, 1, 10. Okay, I can't have a side that's 10 and then connect it with 2 other sides that are 1, right? So that's an invalid triangle. So I want to make up an IDM for this. And because we're using this interface-based mechanical approach, I'm looking at these saying, okay, it's an integer, and it's an integer, and it's an integer. So these are all going to have the same domain model. And what should this domain model be? Well, I'll start out not thinking too hard, and I'll say, well, it's an integer, so let's make it, what's the relationship between the value and 0? And this is actually the same example that I was giving earlier. So I might make up some characteristics, right? Characteristic 1 is the relation of side 1 to 0. And so side 1 might be greater than 0, or it might be equal to 0, or it might be less than 0. And the same for side 2, and the same for side 3. So how many possible tests do I have? Well, I've got side 1, I've got side 2, I've got side 3. They've each got 3 choices. That's 3 times 3 times 3, 27 choices. Now, as it turns out, most of the resulting triangles are invalid, because any triangle with a negative side is invalid, because that's not a triangle. And arguably, any triangle with a 0 length side isn't a triangle. That's just a line. And so it turns out that of these 27, 26 of them are invalid, and only one of them is a valid triangle. So that feels like a shortcoming to me, right? That feels like, okay, I put this domain model together, and 26 of the 27 tests result in invalid triangles. Like, I've got a bad feeling about this, right? This doesn't seem like a very useful partitioning. So let's refine it a little. How might we refine it? Well, without thinking too hard about it, let's put in a special case for 1, because just like 0 is often a special case with integers, 1 is often a special case. So we're going to add another block to each of these partitions. So it's going to be greater than 1, or equal to 1, or equal to 0, or less than 0. And we're going to apply that to all the sides. Now I have 4 times 4 times 4. I've got 64 tests. And at least more of them are now valid values. So I think we've made an improvement to our input domain model. Now, alternatively, we can take a functionality-based approach. In our functionality-based approach, we're thinking about, what does this thing do, right? This triangle class, what is it doing? Well, it's taking in the lengths of sides, and then it's going to tell me what kind of triangle it is. So rather than caring about the length of the sides, maybe what I really care about is what kind of triangle I'm handing it, to make sure that it tells me it's the right kind of triangle, right? So this requires some more design effort. It lets me incorporate domain knowledge, right? Now I know, I have some meaningful knowledge about what this thing is supposed to be doing. I'm going to incorporate that knowledge into my input domain model. I might use relationships between the parameters instead of using the parameters directly, and you'll see that on the next slide. I might be modeling based more on the requirements and less on the implementation. And the same parameter might appear in multiple characteristics. Let's skip over that for now, because I think we come up with an example of that in a little bit. So let's go back and think about our triangle class again. So all 3 of those parameters, when I consider them together, they represent a triangle. So my input domain model could combine all those parameters, right? Side 1, side 2, side 3. I don't have to think about them separately. I can be a little more abstract and say, what I care about is the type of triangle. And so what's the type of triangle? So if my characteristic is I care about the type of triangle, then I have scalene, isosceles, equilateral, and invalid. Seems good. I think I'm on the right track here. Although there's a small problem in that equilateral triangles that have 3 sides the same also by definition have two sides the same. So they are by definition also isosceles triangles. So now if I have an equilateral triangle, it actually fits into two of these blocks. So my blocks are not disjoint. So I have to make them disjoint. And I can make them disjoint just by taking the isosceles category and qualifying it a little bit and saying, oh yeah, isosceles, but not equilateral. And now I'm back to the point where any particular set of three sides will fit into one of these four blocks. Now, it turns out that that gives me only 4 tests, right? Because I need to provide the system with a scalene triangle, an isosceles not equilateral triangle, an equilateral triangle, and an invalid triangle. I guess we could think whether 4 tests are really enough or not. But I do have a relatively infinite number of values that I can use. So for example, these actually combine, right? For scalene 4, 5, 6, that'll give me a scalene triangle. But there are an essentially infinite number of other integer combinations that will also give me a scalene triangle. 3, 3, 4 gives me isosceles but not equilateral. So does 5, 5, 4. So does 6, 6, 4. 3, 3, 3 gives me equilateral. So does anything with all three the same. 3, 4, 99 is invalid. I can't close that triangle. And there are many of those available too. So I could also look at this from a slightly different way and say, well, instead of having, let me go back a second here. Instead of having one characteristic that has 4 blocks, let me instead have 4 characteristics, each of which is binary. So this is a scalene triangle, true or false. This is an isosceles triangle, true or false. This is an equilateral triangle, true or false. This is a valid triangle, true or false. Now, because these are different characteristics, not different blocks, different characteristics. Characteristics don't have to be disjoint. All right, so if I have 3, 3, 3, that's an isosceles triangle, true. It's an equilateral triangle, true. It's a valid triangle, true. And I can apply constraints. I can apply some constraints to my model to ensure that when I have an equilateral triangle, then by definition, it's an isosceles triangle. When it's not a valid triangle, then it's not one of these others either. Now, for this particular input domain model with triangles, taking this approach probably doesn't really help us much. But there will be cases that you might run into where you think, you know, I could break this up into blocks, or maybe I should go the other way and consider breaking it into characteristics. And you may find that one works better than the other as far as producing useful tests. So you can have multiple input domain models. If you're looking at a program or a system, it might have hundreds, it might have thousands of parameters overall. Probably the best approach is not to say, I'm going to create an input domain model that contains everything, right? I'm going to create an input domain model that contains all of the possible data for a physician and all of the possible data for a patient and all of the possible data for a hospital and all of the possible data for every drug. That seems impractical. So I might break that up into smaller input domain models so that I can kind of test things piecewise. And that will just be a more manageable way to approach my testing problem. All right, so I promised you that tonight we would start with criteria, actual criteria. And here we go. Here's our first one. All combinations coverage, right? We're going to use criteria to choose sets of values to give us, hopefully, effective tests. And so the most obvious one is the one we've already talked about, all combinations. I'm going to take all combinations of all the blocks from all the characteristics, and I'm just going to multiply it all together. And how many does that give me? Well, it's the product of the number of blocks in each characteristic. So for triangle, using the length of sides where I defined it as greater than 0, greater than 1, 1, 0, and less than 0, that would give me 4 times 4 times 4, or 64. Is that too many tests? Is it not enough tests? That's something I'd want to think about. Only 8 of the tests, only 8 of those 64 tests are valid. So does it make sense for me to actually test all combinations when, 48 of them, 56 of them are going to be invalid? Maybe not. But all combinations, it's easy to compute, even though it's often hard to implement because there are often so many possible combinations. So here's an example of all combinations coverage. We're going to go a little abstract here. And so I've got 3 characteristics, A, B, and C. A has 3 blocks. I don't care what they are, it just has 3 blocks. B has 2 blocks and C has 2 blocks. Now I want to point something out in this table. If you look over here on the right side of the table for B and C, I have denoted these with dash dash. And all I mean by that is there isn't another block for B and for C. There's only 2 blocks. But for convenience, it's nice to have a rectangular table. It kind of gets hard to draw them when they're not rectangular. So that dash dash just means there's nothing else out there, right? There's only 2 blocks for B and C. So what are all my possible combinations? Well, okay, you can go through them as well as I can, right? A1, B1, C1, A1, B1, C2, A1, B2, C1, etc. Right? All the different combinations. And so there should be, for this, there'll be 3 times 2 times 2, so there should be 12, 2, 4, 6, 8, 12. 12 is not too bad with a small, a small input domain like this. I have another one, another criterion that I can apply that will give me a reduced number of combinations. And I'm going to reduce that number of combinations in this each choice coverage by saying, well, I need to have a set of tests that use a value from each block of each characteristic at least once. And so the number of tests is the number of blocks in the largest characteristic. I've got an example coming on the next page, so don't panic yet. So for triangle, that would end up being 4. And here's some example values. Those don't look like especially good tests to me. But how does that work? How does that each choice work? So for each choice, going back to the same domain model, A1, A2, A3, B1, B2, C1, C2. And I need to make sure that each of those appear in at least one test. So does A1 appear in a test? Yep, sure does. It's in the first test. And B1 is in the first test, and C1 is in the first test. And A2 is in the second test, and B2 and C2 are in the second test. And A3 is in the third test. And then I don't have anything else that I need to use for B or for C, but I have to pick something because my test requires all 3 characteristics. So I'll just go back and I'll reuse whatever ones are handy. I can select them randomly. Maybe some of them are easier to implement than others. But in this way, I have each block being used in at least one test. So that's each choice. If we go back and think about all combinations, let's scale down all combinations a little bit, but let's still continue to kind of use that, different permutations kind of thing. What if we combine values from one block with values from other blocks in a pairwise manner, right? So pairwise coverage. So we're going to say that a value from each block in each characteristic must be combined with a value from every block in every other characteristic. Let's see what that looks like before we dig into the math of how many that works out to be. Same input domain model. Now what I'm saying here is, okay, I have to have A1 with B1. And I have to have A1 with B2. And I have to have A1 with C1. And I have to have A1 with C2. And I have to have A2 with B1 and with B2 and with C1 and with C2, right? And so you can see, pick any 2 things up here. Well, not like A1 and A2 because those are from the same characteristic, but pick any one thing from one characteristic, and it has to be paired up with every possible choice from the other characteristics. And so this gives me a lot of combinations. However, I can actually implement this number of combinations in a relatively small number of tests. So here is a possible set of tests. There are others, but here is a possible set of tests that satisfies all these combinations. So do I have A1 and B1 in here? Yep, that's in the first test. Do I have A1 and B2? Yep, that's in the second test. Do I have A1 and C1? Yes, that's in the first test. All right, so my first test covered 2 of these test requirements. Do I have A1 and C2? Yep, that's in the second test. So now I've covered 4 test requirements with 2 tests. So you can see how we're pairing up each possible thing, but then we can kind of combine the tests to make this very efficient. If we wanted to, we could extend pairwise, right? In pairwise, we said we have to have every combination of any 2 things. In T-wise combinations, we're going to say, I have to have every combination of any T things. So any combination of every 3 things, or any combination of any 4 things, or any combination of any 5 things. This is a great way, given a complex input domain model, this is a great way for me to turn the dial up or turn the dial down, right? If I have an input domain model with, I'm not going to do the math in my head, a lot of characteristics that have a lot of blocks to them. Well, I could get a fairly low number of tests by going pairwise, right? 2-wise. If I feel like I'm not satisfied that that's enough tests, I want to see more tests. Okay, I can turn the dial up. I can go 3-wise, right? Pick every triplet, or pick every quadruplet, right? 4-wise or 5-wise, until I get the number of tests that I want. Now, the number of tests tends to scale exponentially as I do this, right? The graph goes way up as I go. So how good are these approaches at finding faults? Well, as I take the number of things that I'm considering and turn it up, I find more faults. So this was a study done by NIST, the National Institute for Standards and Technology. They looked at 5 different fairly large applications, right? A medical device, a browser, some sort of server, some sort of NASA thing. I don't know what these were, although their report does describe them if you actually are that into reading the report. And they first said, okay, what if we test one thing at a time? That would be each choice. And then these graphs show how many of the existing software failures that they knew were in here were found. And the answer was, well, you know, doing each choice found some. I mean, maybe a lot, maybe not, depending on how you look at it. Going to pairwise found a lot more. Going to 3-wise found somewhat more. Going to 4-wise, 5-wise, 6-wise found slightly more, right? Diminishing returns. It found incrementally more for a lot more effort. All right, I got a question in the chat. Sorry, it's hard for me to look at everything at once. I hope it hasn't been sitting there for too long. Do the tests have to be entered manually, or it can be done automatically, similar to a parameterized test? It's usually fairly easy to automate this. Once you define what the, it's a manual process to identify the characteristics and to partition them into blocks and to decide what's in each block. Once you've done that, you can usually use automated techniques, and I mean, one of my favorite techniques is just Excel, to actually generate test cases based on what you've defined there. All right, we've got one more here. Actually, I think we've got 2 more criteria in here. All right, I promised you criteria, and here they are. Base choice coverage. When we're doing base choice coverage, we're going to use our domain knowledge of the program, right? We understand what this program does. We understand why some values matter and some don't. And in base choice coverage, we're going to select a base choice block. Okay, that's a selection for each characteristic. We're going to select one block of that characteristic that we say is the base choice. And by base choice, we mean it's kind of like the standard one that we're going to keep going back to. And then we're going to combine that. We're going to combine all the base choices from all the characteristics to make our base test. And then we're going to vary one at a time the blocks in each of the characteristics to come up with the rest of our test set. So a couple of rules here. That base choice test, that base choice where we said, okay, here was the base choice in each characteristic, now we're going to combine them all, that must be a feasible test. What I mean by that is that the values in those base choices must all be compatible with each other. How do I decide on a base choice? It might be the most likely value, it might be the most common value, it might be the simplest. If there's some ordering, it might just be the first one in the order. A happy path test, right, makes a great base choice. So if one of my parameters is an object, and I decide my object can be null, or an object of the correct class, or an object of a wrong class. Well, object of a correct class, that's the happy path test. That'll probably make a good base choice. And that base choice is a critical design decision. You should be prepared to explain and document why you chose that. And if you make a poor choice on your base test, so for example, let's say, again, I've got a lot of parameters and one of them is object, and I say, oh, you know what? Null is going to be my base choice. Well, you're probably going to find that you have an awful lot of infeasible tests, because when the object is null, often none of the other values matter. So let's take a look here. What does it mean to put together a base choice test? So I've got my same input domain, and I'm going to decide, in this case arbitrarily, that A1 is my base choice block and for A, and B1 is my base choice block for B, and C1 is my base choice block for C. And so I get my base choice test, A1, C1, A1, B1, C1. Then I go through all my variations on A, right? What other values of A do I have? I'm going to hold B and C constant, and I'm going to iterate through my A values. So I'm going to go A2, B1, C1, A3, B1, C1. Then I'm going to iterate on my values for B. I already used A1, B1, C1, so now I'm going to go A1, B2, C1. And then I'm going to iterate on all my values for C. And so we're going to slip in C2 while keeping the others the same as the base choice, right? So I'm taking the base choice test, and then I'm only varying one characteristic at a time and iterating through all of the other values for that characteristic. And together, this makes a base choice test set. I can also, and I might do this especially if I felt like, okay, I built myself a base choice test set, but I'd like to have more tests. One way to get more tests is to do multiple base choice coverage, and this is exactly what it sounds like. I'm going to pick 2 or more things as my base tests, and then I'm going to vary things in exactly the same way all over again. And I do have an example for that. So I'm going to pick A1, B1, C1 as my first base choice. And then I'm going to do the same kind of variation I did before. Okay, I'm going to iterate my way through the other values for A, and I'm going to iterate through the values of B. I'm going to iterate through the values of C. Then I'm going to pick another base choice. So my new base choice is A3, B1, C2, which I may have picked arbitrarily, or I may have had a reason to think that that was a special case. Now I'm going to do the same exact process. I'm going to iterate through my other choices of A, then I'm going to iterate through my other choices of B, and then I'm going to iterate through my other choices of C. And you can see now I've gotten myself more tests. If I want still more tests, I could come up with another base choice and then iterate on that again. And I can build my tests up to the point where eventually I reach all combinations. And you can't really have more than all combinations, right? That's your upper limit. Okay, so coming towards the end of this, some combinations are infeasible. So for example, I couldn't have a test combination where I have a side less than 0 and a scalene triangle. Because if I have a side less than 0, it must be an invalid triangle. And so I represent this by constraints on my domain model, my input model. And generally I've got two kinds of constraints. One constraint is if I pick a block from one characteristic, then I can't combine it with some other block from another characteristic. Or if I pick a block from one characteristic, I can only combine it with a specific block from another characteristic. And how we deal with those constraints depends on the criteria we're using, right? Those constraints will help us to identify things that are infeasible. So if I said, yeah, I don't have a good example off the top of my head, but let's assume we've got this first kind of constraint. If I pick something from A, right, if I pick A1, then A1 can only match. Okay, I misspoke. I'm going to take the second one. A1 can only match with B1. So if I produce a test that's A1, B2, that violates my constraint. That's an infeasible test. So what do I do with it? Well, if I'm using all combinations or pairwise or T-wise, I take that infeasible test and I drop it. I just throw it away. If I'm using base choice coverage, then I'll change the value of one of the other characteristics to try to find a feasible combination. If I eventually can't find a feasible combination, then I'll throw it away. So let's look at an example of this. So I've got this find element. It takes a list and an object, and it'll either return the object if it's in the list, it'll return true if it's in the list, it'll return false if it's not in the list, or it'll throw a null pointer exception if the list or the object are null. So I could break up characteristic A, the length and contents of the list. I could break that up into a couple of things. I could say, well, the list is equal to one element, or it's greater than one element and it's unsorted, or it's greater than one element and it's sorted, or it's greater than one element and it's all identical. This may not be complete and it may not be disjoint, right? It's just kind of my starting point here. And characteristic B could be my match, okay? I could say characteristic B is my object, but I'm not really that concerned about the object itself. I'm concerned about the relationship between the object and the list. So what I'd like to say here is that either the object is found, right? The element is found. I'm sorry, the element is not found, or it's found once, or it's found more than once. And again, this dot dot out here just means I don't have a fourth partition, a fourth block. So if we look at this, I've got some infeasible combinations. So AB1, okay, list is one element long, and BB3, element is found more than once. Well, if the list is one element long, I can't find the element more than once. So that's an infeasible combination. I couldn't come up with a test case for that. Or AB4 and BB2. AB4, it's greater than one in length and they're all identical. And BB2 is element was found once. Well, if they're all identical and there's more than one of them, then I can't find the element just once. So that's another infeasible combination. So I hope that illustrates what I'm talking about infeasible combinations. So there's a reason why we talked about subsumption last time. We're going to revisit this pretty much every week. How do these criteria that we talked about here compare today? So at the bottom is each choice coverage. each choice coverage is subsumed by pairwise coverage, which means if I satisfy pairwise coverage, I am guaranteed to satisfy each choice coverage. T-wise coverage subsumes pairwise coverage, right? If I can satisfy all combinations of any three things, for example, I'm guaranteed to have satisfied all combinations of any two things. All combinations coverage subsumes T-wise. If I was able to find all combinations of three things, if I was able to find all combinations of all things, then I'm guaranteed I was able to find all combinations of any three things. On the other side of the subsumption graph, we have base choice coverage. If I satisfy base choice coverage, I'm guaranteed to satisfy each choice coverage. If I satisfy multiple base choice coverage, I'm guaranteed to satisfy base choice coverage. And if I satisfy all combinations, obviously I'm guaranteed to satisfy everything else. The interesting thing here is that there is no guaranteed subsumption relationship between, for example, T-wise coverage and base choice, or between multiple base choice and pairwise, right? We can't guarantee that that's the case. And so if you want to think that through some more and are looking for, some participation points, start a Piazza discussion on that topic and either prove I'm wrong, in which case, yes, then I think we'll probably award you an honorary doctorate right out of the box, or show me a case that demonstrates why it's false, or excuse me, show me a case that demonstrates why multiple base choice doesn't subsume pairwise, or why T-wise doesn't subsume base choice. So, be an interesting discussion topic. All right, we are just about there. So our ISP, our summary here, input space partitioning, fairly easy to automate even without using any kind of automation tools, right? We can do it successfully, especially in simple to medium cases without having complex tools. We've got some convenient ways to increase or decrease test cases. I can go from each choice to pairwise, or pairwise to T-wise, or base choice to multiple base choice, right? I can dial it up or I can dial it down. It's applicable to all levels of testing, unit testing, integration, system, everything. And it's based on the input space of the program, not really on the functional implementation of what happens. All right, any questions on our input space partitioning? All right, then we'll go ahead and take a break. It's 6:12 now. Let's take an 8-minute break. We'll come back at 6:20, and I'll give you a short brief on the assignment, on the exercise, excuse me, for today, and then send you off into your groups. So see you in 8 minutes.